Yeah, faster linear algebra using treewidth. This is joint work with Daniel Greer. The two of us normally work on quantum algorithms and complexity, but this project spun off of one of those, and it's a purely classical algorithm for speeding up solutions to linear systems, and we get to use this nice treewidth graph parameter. So we're solving linear systems of equations. AX equals B. This is very basic Math 136 stuff. I'm going to assume you all know how to solve a linear system. You probably have happy memories of row-reducing matrices. And we're going to focus not so much on the dense case, but on the sparse case, where most of the entries here are 0. And because there's so much missing from this matrix, well, it's a special case of the general one, right? So all the same algorithms could apply, but because we're missing input, or there's less input, we're hoping that there could be a speed up. We could solve this system faster than the general case, right? But it doesn't just depend on how many non-zeros there are in the matrix. It depends on their structure, where they occur. And a good way to capture that is with a graph, where there's an edge exactly to encode a non-zero in the matrix, right? And then the whole pitch is that maybe we can solve the system faster when this graph has some nice structure, like it's a tree, or it's a planar graph, or it's close to one of those two in some sense. Then maybe we can get a faster solution. But okay, let's start with how fast can you solve a dense linear system. So Gaussian elimination, you pick a non-zero and eliminate a column, and repeat, and so on. And you get it down to a system that is easy to solve, like a diagonal matrix or an upper triangular matrix. And in the process, you're going to eliminate n-squared entries. Each one is a row operation. You're spending order n work to do that. So overall, n-cubed field operations, right? Now, throughout this talk, we're going to assume field operations are all unit cost. There are fields where multiplying numbers gets more expensive as you go. If the numbers, get larger, think of the rationals, for example. If the numerator and denominator are large numbers, it's expensive to, say, add two rationals. So this is a simplifying assumption. You can pretend we're working over a finite field, for example, or over the reals and working with floating point numbers. Although, speaking of floating point numbers, we're going to assume all our operations here are exact. I don't want to have to deal with numerical stability or precision or any of that, so maybe finite field is best. Okay, so Gaussian elimination is n-cubed. You can go faster than that, even for dense systems. You've probably heard of fast matrix multiplication. This idea that you can multiply two matrices faster than the naive n-cubed bound, and we say the optimal exponent for this is omega. And people work very hard to lower this bound. The current record is 2.37 something, but they update it every year or two. And it's not just matrix multiplication. You can do a whole big chunk of linear algebra in n to the omega time. There are reductions here that say you can do, well, most notably for us, linear system solving in n to the omega time, but you can also get an LSP decomposition, which is a little more niche, but it implies rank, determinant, inverse, null space. All of these common linear algebra primitives you can get in the same time, right? And I guess the rule of thumb here is that if you can do it with Gaussian elimination in n-cubed time, there's probably some way to compute the same thing in n to the omega time. Okay, so that's the best for dense systems, but let's go look at a sparse system, and we'll construct one from scratch. Suppose we have a line of vertices, and we put a variable at every vertex. And we'll also put a constraint. But the constraint is local. It only acts on the vertex and its immediate neighbors, or the variables at those positions. So a whole bunch of equations on consecutive triples of variables, except at the ends. And so if you write this out as a matrix, it looks like this. It's what's known as a tridiagonal matrix, because obviously the three main diagonals here are the only place you have any non-zeros, and well, yeah, that's the reason. So this is a real family of matrices that people want to be able to solve. It shows up in scientific computing applications and, you know, toy physics problems and splines for computer graphics. And it shouldn't surprise you that, you know, this is a very sparse system. There's a lot of structure. We should be able to solve it faster. And indeed, there's a linear time algorithm for this. And that's the optimal. You can't go any faster because your input and output are both linear size. Okay, a little generalization of that. What if I went from a one-dimensional grid to a two-dimensional grid with the same sort of system, a variable at every vertex and local constraints on the neighborhood of a vertex? Well, in that case, there's an entirely separate algorithm, nested dissection, which solves this system, and indeed any planar linear system, in n to the omega over 2 time. So a clean quadratic improvement over a similar dense system of the same size, right? So, oh, and there's a technical caveat. It needs to be symmetric or something. That's not a big deal. Anyway, these are two families, right? I guess a path is a family of graphs, and planar graphs are a family of graphs. And we could try to come up with algorithms to speed up all sorts of systems on other families of graph, right? But there's a lot of them. If I did that, this talk would go well past midnight. So we want to get one algorithm that gets all of these cases at once. So an algorithm that solves a sparse linear system depending on the size of the system, which we'll say is just the number of variables plus the number of constraints, call it n, and a parameter for the graph, you know, some score for how good that graph is in terms of speeding up linear systems. So specifically, we're going to use the tree width of what I'm going to call the constraint graph. There's a couple things to define there. So the constraint graph is the obvious graph you define. Here's your matrix. You construct a variable for every vertex, or sorry, a vertex for every row and column, and then you connect them in a bipartite sort of way if there's a non-zero entry at that point in the matrix, right? So you get a sparse matrix. I know it doesn't look sparse, but there are exactly as many edges as entries in the matrix, right? And then the tree width, we'll define it a little more properly in a second, but it supposedly measures how tree-like a graph is. And the scale here is 1 being an actual tree, and n minus 1, the polar opposite, being the complete graph. Okay? So tree-like could mean a lot of things. As a computer scientist, I think of it as measuring sort of how well a certain class of algorithms that operate on trees can be applied to this particular graph, but there are other ways to look at it, lots of other ways to look at the tree width. And one of the things we like about it is that it's been around for, I don't know, 40 or 50 years, and people have worked out for various families of graph what the tree width is. So cycles, outer planar graphs, series parallel graphs all have tree width 2. When you move to the planar graphs or some other different types, notably H minor free graphs, the tree width is apparently square root n. And then there are graphs where they're just too general, like a complete bipartite graph or an expander or something like that. And there the tree width is order n. So for those graphs, we're not expecting a speed up, but for planar graphs, cycles, series parallel graphs, all those, we should be able to solve the system faster. Okay, so before we get into our result, there's one piece of prior work.
What is the degree of expanders that have linear tree width?
I don't know, I assume 3 is enough.
Oh, okay.
Like, yeah, very sparse graphs. Maybe it's n over log n, but I think it's linear. Okay, so there was one paper, 2018, that tried exactly what we're doing here. Before, they had a result. They had several results, and one of them was solving a linear system of equations in time linear in n and cubic in the tree width. Okay? Let me just switch to our notation with a t. So is this a good result? You know, is this the right runtime for the problem? Well, it's polynomial in n and t. That's a good start. And linear in n. So if the tree width happens to be a constant, like in that tridiagonal case we saw, then you get the optimal performance. So it's recovering that algorithm. That's excellent. On the other hand, if you plug in tree width on the order of n, if you're working on a dense graph, then it gives you an n to the fourth algorithm. You know, it's worse than Gaussian elimination. So that's not what you want. Now you could say just don't apply it on systems like that. Like, what are you doing? But it's a hint that we've got the wrong complexity for the problem, right? We should have an algorithm that scales cleanly between those 2 points. So the authors themselves recognize this problem. The exponent on t is not right here, and they had a couple different ways to fix it. Their problem is, or their paper is full of open problems. There's about a dozen of them. And 2 of them can be read as talking about this particular question. So one option is you could save a factor of t. They managed to do that for a related parameter called the path width, but they couldn't make it work for tree width. Or, you know, this is a linear system solving algorithm. You have to assume that t cubed is coming from solving some matrix, and maybe you could replace that, however you're doing it, with a fast matrix multiplication algorithm. But they couldn't make either of these work. And unfortunately, you need both in order to get what we think is the optimal complexity. So that's what we're going to do in our algorithm. We're going to convert this 3 to an omega, and then we're going to save an additional factor of t on top of that. And our algorithm has some other, I don't know, minor advantages. Sometimes in these linear system solving things, you assume that the problem is square or full rank or symmetric or PSD or only over the reals or something like that. We'll take any linear system you want, rectangular, over a finite field, whatever. Underdetermined or overdetermined, it's all fine, and produce a solution. Another sort of advantage is that internally this algorithm is using a dense linear system solver as a subroutine. So if you want to swap that out for something else, you absolutely can. To get the best performance, you use, you know, these fast matrix multiplication algorithms, but you could equally replace it with Gaussian elimination, or if you wanted to do it in shallow depth, maybe you use a parallel algorithm for solving a system, or, and I wouldn't recommend this, you could use an approximate solver and just let the error accumulate, maybe get a wrong answer. Anyway, there's all different things you could do there. Anyway, the outline here. The rest of the talk, we're going to start by introducing tree width. I may have done too much of this. I'm going to assume there's some experts that actually know about tree width here, but most of you do not. So if you all learn something and the experts have a little nap, I see that as a win-win. So we're going to define it and introduce a little planar coloring example to illustrate what an algorithm looks like with the tree width. Then we'll get back to solving linear systems and the details of the algorithm. That's a tiny bit technical. We'll talk about the complexity of it, and we have a lower bound. It depends on a conjecture, but we have at least an argument that this is the right complexity for the problem, that you can't do better. And then if there's time after that, I'll talk about what I would ordinarily call future work, but we're working on it right now, so it's work in progress. Okay, so tree width then, unless there are questions.
I have a basic question. So is it true that the time complexity of matrix multiplication and solving linear systems are equal to each other?
I think so, yeah. It might get weird if omega is 2 or something, then there are log factors in the reductions for reasons, but I think generally the exponent has to be the same for the 2 problems. There are reductions either way. Okay then, tree width. So to define tree width, you have to talk about tree decompositions. That's the object being studied here. And for that, we need an example graph. So here's the Wikipedia example for tree width. And here's the A tree decomposition. So it's a brand new graph, and the first thing you should notice is that it's a tree. That's important for tree decompositions. They're all trees. The second thing you should notice is that it's labeled with subsets of the original graph. It happens to be triples here, but there's no rule that says that has to be the case. There are, however, what I'll call 3 laws of tree decompositions. Okay, 3 rules for how you're allowed to label this thing. I'll run through them. So the first law is that all the vertices in your original graph have to show up somewhere. So here they all occur somewhere in the decomposition. Some of them only once, some of them multiple times. That's all perfectly normal, perfectly fine. But it does lead into the second law, which is that if a vertex occurs many times, then it has to be connected. The nodes containing it have to all be connected. And I mean, they're on a tree, they're connected in that sense, but if you remove the nodes that do not contain B, then you still have to be able to get between them. So if I took out this, this node here, that would disconnect the B's. You can't move between them anymore, that's not allowed. And this isn't just for one vertex, it's for all of them, so you can verify that this is true for this particular tree decomposition. And then the third law, we haven't used the edges of our graph yet, so we have to do something with them. And it says that for every edge, both of the endpoints must occur together somewhere in the tree decomposition. So this edge BE right down the middle, that means that B and E must occur together, and sure enough, they're in that node, and you can pencil in a little edge. And you can do this with all the rest of them as well. You can take each edge and find a home for it somewhere in the tree decomposition. And that's it. That's the definition of a tree decomposition. It's just a tree labeled with these subsets of vertices such that every vertex has to appear, every edge has to appear, and there's this connectivity on the vertices. Okay, so then tree decompositions are not unique. This is a tree decomposition of our original graph, but so is this. You can just dump all the vertices into one node, and technically that satisfies the definition, right? All the vertices are there, all the edges, connectivity is trivial, everything checks out. But we obviously prefer the one on the left to the one on the right. It tells us more about the graph, it's just generally more interesting. And one of the ways we formalize this is with the width of the tree decomposition, which is defined to be the size of the largest node, the number of vertices in it, minus 1. Minus 1 is for annoying historical reasons. In my opinion, it's a bit of a mistake, makes everything a little more awkward, but we're stuck with it. So the decomposition on the left has width 2, because all of the nodes have 3 vertices in them. And on the right, it's width 7, and we prefer the lower width tree decomposition. So there you go. And then we use the width to define the tree width. It's a little confusing. Width is for the tree width is for the graph, and it's defined to be the minimum width of all possible tree decompositions for that graph. So in this particular graph, we have a tree decomposition of width 2, and you can show that there's no tree decomposition of width 1. Basically, you have to be a tree to have a tree decomposition of width 1. So in this case, we can work out the exact tree width for this graph. And that can be somewhat difficult. As you can imagine, optimizing over the space of all possible tree decompositions is not easy, right, to find the minimum one. In fact, it's known to be NP complete. So if you want to find a tree decomposition, an optimal one, it can be a little bit challenging. And that's a little bit of a problem for the algorithm because we do need a tree decomposition in order to run it. It's not enough to just know what the tree width is. We need the actual tree decomposition in order to execute it. So you have to rely, well, you can get the tree decomposition however you choose. One option is approximation algorithms, of which there are many. So this table is giving you the approximation factor, the running time of the algorithm in terms of t, and the running time of the algorithm in terms of n. Because algorithms to find approximate tree decompositions themselves depend on the tree width. which is a little bit interesting. Anyway, there's a lot to choose from. If you sacrifice a bit in your approximation factor, you can even get a polynomial time approximation algorithm, and that's good enough for us. For the rest of the talk, we're not going to really get into where you get your tree decomposition. We're just going to assume we have one. Oh, and for planar graphs, the situation is a little bit different. Planar graphs and a couple other families, you find a tree decomposition by separators. You cut the graph in half with a small set of vertices, and then you use that to build a tree decomposition recursively. Okay, so with all of that, we have a formal definition now. But maybe it's not clear how you would apply this in an algorithm. Like the tree decomposition ends up getting used as a sort of a schedule for how you process the graph. But even with that hint, it's not necessarily obvious how you speed up an algorithm. So let's do a quick planar coloring example. Here's a planar graph, right? Nice and familiar. And by the four-color theorem, we should be able to color this with four colors. And indeed, here's a proper four coloring of the graph. But what if we wanted to count the number of four colorings, right? Just out of curiosity, for this particular graph. Well, counting colorings is in general sharp P complete. Our best algorithms for this are exponential time, and maybe on a smaller graph we could get away with that, but 49 vertices is kind of a lot to plug into an exponential. So we need to use the tree width, which was the point all along to illustrate how tree width can help. So for this particular map, I happen to have a tree decomposition of width 6. So here, it's actually even slightly better than a tree decomposition because there's no branching. It's just one long path, and we'll come back to that at the end. But what are we supposed to do with this, or an actual tree decomposition? How do you use that? Well, the general strategy is to start at the leaves and construct partial solutions. And then you can take those and, yeah?
Sorry, just a small question. How does the main needed for tree decomposition because it doesn't help any of the reactions?
We could delete that and it would be fine, but it's also okay if we have it. I mean, it's also in the one above it, but you'll see in a second I end on a single vertex set with main in it. Anyway, what was I saying? Right, yeah, okay. We take the tree decomposition. We want to produce partial solutions at the leaves. In this case, it'll be like partial colorings, and build those solutions up as we move up the tree, add more vertices, merge solutions, and then at the top, we have our answer. So we'll see that in action. And to start, we look at a leaf. And the leaf in this case is these 7 particular vertices on the west coast. And we're supposed to produce partial colorings, right? And, well, we can just brute force it. 4 to the 7, the upper bound on the number of possible colorings is only 16,000. So the computer can just run through all of those, no problem. Okay, and as it turns out, only 240 of them are proper colorings. So you can make a massive table, 7 columns for the different states versus 250 rows for all the colorings, right? Why not? And we're supposed to extend this to larger colorings, but the tree decomposition says no. We're not going above 7 states at a time. If you want to add more, you're going to have to cut some of them out. And in particular, it tells us this is the current node, this is the next one. The only states in common are these 3. So you need to get rid of the blue states here before you can introduce the red ones. So what does that mean? Why can we get rid of these? Well, because for these 4 states, we've seen all their neighbors, right? Like Washington, for example, the only states next to it are Idaho and Oregon. So if we're adding more states, we never care about how Washington is colored. We just need to know how many colorings there are for Washington and those others. So in this massive table that we constructed, we can get rid of 4 of those columns and replace them with a number, right? How many ways are there to color those 4? So this is saying for each particular coloring of Arizona, Idaho, and Utah, you can get 8 colorings, compatible colorings of the remaining ones. Okay? And then we've we've reduced to 3 states, right? And we have room to bring in some more. So we do that, we brute force over all the colorings of those, and then by the same logic, we can drop 3 of them. And then we have room to bring in 3 more. And you can work your way, slowly but surely, never using more than 7 states, to Maine, which is why I had Maine at the end. And the table there looks like this. You have 4 colorings of Maine and 6.4 trillion colorings of all the rest of it, compatible with each one. So you can easily extract a grand total from that. This is how tree-width algorithms typically work. Okay, and this is the right answer. I coded it up because I was actually curious. Anyway, there was a point, though. We used a path decomposition for this, right, which was not a general tree decomposition. What would it look like if we had branching? Well, if we had branching, you get a table for some part of this map, and for its sibling, you would get a table for another part of this map. And then what you're asked to do is take those 2 tables and merge them to produce a table for the 2 of them combined. And this is a new operation, one we didn't have to do, but it's not difficult, especially since you're guaranteed that the interiors of these 2 regions are disjoint and non-adjacent. So you don't have to worry about any interactions between them. It's guaranteed by the various laws of the tree decomposition. So, okay. Now we have to get back to linear system solving, with this as a sort of an example in mind, an intuition for how we want to do this. Because linear systems are a bit less clear, a bit less intuitive. And there are some challenges in doing that. Like, for example, we made a big deal of all these partial solutions that we want to construct. For coloring, it's very clear that you just use partial colorings. That's obviously what a partial solution is. But for linear systems, it's a little less clear what a partial solution to a linear system is. Do you just drop some of the variables and some of the constraints? How do you pick? So we're going to have to figure out what that looks like. And then even once you have a concrete idea of what you're computing at every node of the tree decomposition, you still have to figure out how to do it, how to get from the solution at one level to the solution at the next. And there's some difficult manipulation of affine subspace. Well, not difficult, but there's some work to do. And then at the end of this, we still have to talk about complexity. For this example, we didn't do anything. It was done in time for the talk, so that was good enough. But for the linear systems, we're going to have to get a quantitative bound, right? This nt to the omega minus 1, we have to argue that. Okay. Any other questions? Okay, so then linear systems. If we're looking at a set of solutions to a linear system, it's going to be an affine subspace, right? For the whole system, this is how it works out. And affine subspaces you can represent implicitly as mx equals b like this, or there's a theorem that you can equally represent them with a more generative, concrete sort of representation, a point in the space and generators that move you around inside the affine space. And what we're going to do is, well, okay, the plan is to construct an affine subspace for each and every node in the tree. We just have to figure out what that affine subspace is. And as I said, we're going to take some cues from the coloring example. For a start, I need a little bit of terminology. See, there's 3 different kinds of vertex here in the middle of this computation. There are the purple vertexes, the one in the node we're actually looking at. There are the blue vertices, the ones that we've already seen. We've sort of worked through them already. And then there are the red vertices that we have yet to process. And if we're looking at a tree, we can do the same sort of thing. There are the vertices in the node we're currently looking at. Let's call them boundary vertices. There are vertices in the subtree below. Let's call them internal. And there are vertices outside, possibly in siblings of the tree. We'll call them external. okay? And this is a partition. You're in exactly one of these three cases. Again, this is an easy thing to prove with the tree laws, tree decomposition laws. Okay, another cue we're going to take from coloring is that the partial solutions we looked at only involved the internal and boundary vertices. We didn't bother with the external ones. We haven't seen those yet. We're going to ignore them. So now we're going to try and extend that idea to the linear system. So here's the linear system, the important data, M, X, and B, right? And I've drawn it in this sort of unusual configuration so that the rows here correspond to variables, or sorry, columns correspond to variables, and the rows correspond to constraints. And you'll recall that in our constraint graph, rows and columns, or constraints and variables, were vertices. And we just talked about how the vertices are partitioned into these three sets. So you can partition these into internal, boundary, and external variable vertices, as well as internal, boundary, and external constraint vertices. So we've got a 3x3 matrix here. And we argued that the external stuff shouldn't matter. We should just throw all of this away. So we're going to define our affine subspace, our subproblem that we're solving at each node, in terms of the remaining data. What's that going to look like? Well, presumably, we want to solve for U transpose and V, well, U and V, the variables there, subject to whatever constraints we have. The concern at this point is that we may not be able to enforce any of these constraints, right? We don't know what that last block of variables is. This is sort of self-imposed because we were throwing away that part of the matrix, but we'll go with it. And the blocks below it get multiplied by that. So how are we supposed to tell whether this first block of constraints is satisfied or not? And likewise for the second. Fortunately, two of the blocks in this matrix turn out to be 0. And we can prove this. So the top right, internal constraints, cannot interact with external variables. And likewise, external constraints cannot interact with internal variables. So suppose, to the contrary, that they did, that there was a 1 somewhere in this block, meaning that you have an internal and external vertex that are adjacent. That's what it would mean to have the 1. But if they're adjacent, the tree decomposition laws say that they occur together somewhere in this tree. Let's say here, just as an example. And the second law says that the blue vertices, the occurrences of them, are connected. Likewise for the red. So you can connect paths between these occurrences, like so. But if the blue, well, in this case, the blue vertices are going from outside the subtree to inside the subtree, right? Because we said it's internal, and in this case, we're looking at the meeting of the two vertices was outside. So it has to cross the root of that subtree that we're looking at, the current node. And by definition, anything that occurs in the root is a boundary vertex. So contradiction, it was never an internal vertex all along. So it couldn't have been, contradiction. So the point of all that is to justify these two blocks. And we like especially this top right block, because now we can talk about that first block of constraints. We can meaningfully say whether they're satisfied or not, because the last chunk of variables doesn't matter. They're getting multiplied by 0, so it's just, we could define an affine subspace here, all U and V which satisfy this block. And this is close to working, but it doesn't quite make it. Does anyone happen to see what's wrong with this, why we don't want to construct this affine space? The problem is dimension. It's too large. So this is a lesson from the coloring example. You remember here when we reduced a bunch of the vertices to a single number? The boundary vertices in this case are the 3 ones with actual labels, the Arizona, Idaho, and Utah. And all the other variables have to fit into this, the internal ones have to fit into this numeric column. We have to summarize them with just one column. Because if we gave each one its own individual column, there are far too many. We'd run out of space. We'd have a table that's effectively on all the vertices at once you get close to the top. So we need some way to summarize the information in U. This U vector is the problem. The V vertices, the boundary vertices, there's not too many of those. They all fit in one node. But the internal vertices could extend to basically everything. So we need to somehow summarize them, and counting solutions isn't going to work anymore. So okay, where does U get used? Only in this column, by definition. It's clearly not having any effect on these external constraints. It's not important there. It does matter in the internal constraints, but we were already using those in the affine space we defined, right? We already said all of the U and V that we're looking at satisfy AU plus BV equals R. So we shouldn't need to, in the future, do that constraint again, right? Repeat the work we've already done. So the only reason we need U going forward is for these boundary constraints. At some point in the future, we're going to figure out what that last block is. Maybe call it EW. And then we're going to have this constraint that CU plus DV plus EW equals S. And we want to enforce that, apply it to the subspace that we've already got. And so it seems like we need U. Except if you think about it critically, we don't need U, we need CU, which is actually a much shorter dimension vector, right? The height of that is just the boundary constraints of the problem. So together, CU and CV cover all the vertices in the node, the boundary constraints, the boundary variables, and so the entire system is bounded by the size of the node. Right, yeah, okay, so the dimension is exactly what we're hoping for. Okay, so this is the subproblem that we're trying to solve at every node. Compute this affine space. I guess the other half half of this problem is we can compute it at the leaves. That's fairly straightforward. Construct it however you want, brute force or something. But you need to be able to move up the tree. You need to be able to introduce new variables, remove variables, introduce new constraints, remove constraints. And when I say forget, we're not actually like dropping the constraint. That's the step where we enforce the constraint, where we make it apply to the system that we've got. And also merge two branches. So each one of these is a little exercise in linear algebra. I'll do one of them to give you a sort of a flavor of how these go. So let's say we want to forget a constraint. So at some point in the middle of this computation, we've got this one row, and it's currently a boundary row. It sits with that second block, but we want to move it up to the first row and have it take effect as a constraint, because we ignore the boundary constraints and apply the internal ones in our definition. Note that this means the last block has to be 0. You can't do this if there's still outstanding variables. So all of the variables associated with this are present, and this last block must be 0. So what do? Well, you can start with the definition of the affine space before you make the move. And with a little inspiration, one idea you could do is add d transpose v to that top one, or top coordinate. This is just a multiplication by a particular matrix. V is down here, so it's not too much work to add d times it to the top. And we do this because C transpose U plus D transpose V was the constraint we're trying to implement. So starting from that, we just want to set that first coordinate to sigma, right? And then we might as well drop it because it's not encoding any useful information. So there's some linear algebra algorithm that will fix that first coordinate and then drop it for us. And then the last thing you do is you notice that this system, if you combine those two equations, looks a lot like our target, where we've moved the row from the bottom to the top. Like if I put the starting point and the ending point next to each other, you can see that this C transpose U, on the top, it's sort of hanging around with the C part. And on the bottom, we've got C transpose D and sigma incorporated into the A's, the B's, and the R part. So we've moved this from a boundary constraint to an internal one. Okay, so I'm not going to go through the rest. Again, there's linear algebra to sort out here, but it's not very interesting. Let's talk about the complexity. How long does all of this take? Well, okay, one last thing. All of this is working with a system of dimension the size of your node. And as long as you don't, as long as you represent the space with linearly independent generators, you don't gather more generators than you need, the sort of width of the matrix involved is also on the order of the size of your node. So the whole system, everything we're doing here, is operations on matrices of dimension the size of your tree node. So how does that help? Well, if we want to compute the cost of the algorithm, it's just the sum of the cost we pay at every node. And by far the most expensive thing we're doing is solving a linear system. So n to the omega in the size of that node. And if you're pessimistic, you say, okay, all of my nodes could be tree width sized. So then you get t to the omega times the number of nodes. Which brings up a question. How many nodes can a tree decomposition have? Well, unfortunately, technically, arbitrarily many. You can make really silly tree decompositions where a node is repeated over and over again. But in practice, people put their tree decompositions in some canonical form. For example, a nice tree decomposition. This is a technical term. And what it gives you is a new tree decomposition similar to the one you hand it, except where the width is the same. That's a good thing. The number of nodes is at most the number of vertices in your graph. You get a rooted binary tree and a few other structural properties and goodies. And all of this happens in linear time. So it's cheap enough, you should just assume your tree is given to you in this form. It has order n nodes. Okay, well, if we substitute that into the complexity, we run into a problem. Well, I mean, we get a bound, nt to the omega, but it's not the bound we were hoping for. We wanted an additional factor of t on top of this, right? So we're not fast enough. And to fix this, to reduce the number of nodes further, we're going to have to increase the tree width, which for a lot of algorithms, tree width-based algorithms, is not what you want to do. But here it makes a certain sort of sense. So the lemma we get says that for any integer k, you can increase the width from t to t plus 2k, I guess. And in exchange, you get a reduction in the number of nodes. The nodes go from order n to n over k. And so if you put in the right value of k, this is actually an excellent deal. And the idea here is, I guess, the concept of batching. So the worst case for us is a tree decomposition where it's near the tree width, and you're just swapping in one node, swapping out one node, or vertex, and so on. So you get a lot of vertices with very little change between them. Because for us, we're paying on the order of n to the omega for every one of those changes, even if it's just a single node. But we also pay n to the omega if you change out all the vertices in your node, or half of them, or something. So the idea behind this lemma is we want to change out like a third or a constant factor of the vertices in each node from one to the next, so we make a significant difference and justify the cost that we're paying. Okay, so yeah, that's the lemma again. As I said, this is a great exchange as long as you're working with an algorithm that's polynomial in n and t. If you've got an algorithm that's exponential in the tree width, a good example would be the coloring instance that we did. Don't do this, right? Because every increment of the tree width is a factor of 4 increase, and it's just not going to pay for itself. Okay, so what we do then is set k to be t. The width will increase by like 2t, so overall it's maybe triple what it was at the start, but it's still on the order of t. Whereas the number of nodes is n over t, and so we get exactly the complexity we were hoping for, this n t to the omega minus 1. Okay, so, right. The original point of this, just to remind you, was we had these two cases at the ends. If you have constant tree width, like in the tridiagonal case, you can solve it in linear time. Fast matrix multiplication is the best you can do at the other end, and the Fomin et al. Result missed. This is on a log-log plot, so these power law things are actually linear. Whereas this new result that we've got is going perfectly through these points. But I did mention a third algorithm, the nested dissection one. And if you plot it, it ends up below our curve. This is a disaster. We did all this work, and we're still not optimal, really? But it only applies for planar graphs, and there's a bit of a special case there. You see, for planar graphs, the tree decompositions are width square root n. And if you plug in t equals square root n to our algorithm, we are worse than what nested dissection gets. But the thing is, these tree decompositions, the nodes in them are not all the size of the tree width. The one at the root is, and then they sort of tend to decay geometrically as you go down. So you can get sums for like powers of the sizes of these nodes, where effectively only the top entry matters. It's more like having a node with one, or a tree decomposition with one node of width square root n than many. And if we plug this directly into our analysis, instead of assuming this worst case that they can all be as large as the tree width, then we do recover, possibly up to some log factors, I'm not sure, the speed up from nested dissection. So maybe our algorithm is okay after all. And so the last thing I wanted to talk about is a lower bound. Maybe we can argue that you can't do better than our algorithm. And this is going to depend on a conjecture, but, well, okay, it starts with the observation that a t by t matrix, the constraint graph for it, is the bipartite complete graph, right? Order t vertices and tree width t. And we're assuming that this takes t to the omega time to solve. Well, okay, this is not an assumption, this is more the definition of omega. But what if we took a bunch of copies of this graph and just put them next to each other? Don't even bother connecting them, they're just, disjoint copies. If you pick the right number, then you can get a graph that has tree width t, that doesn't grow when you're putting copies next to each other, and n vertices. And on the other hand, the constraint graph, the matrix for which this is the constraint graph is basically a direct sum of many t by t matrices. So our algorithm will solve this particular system, seeing as it's tree width t and linearly many vertices in n t to the omega minus 1 time, right? But on the other hand, this system is describing a whole bunch of completely independent linear systems that we want to solve. N over t of them, they're all size t. And nothing is shared here. The matrices are different, the variables are different, the target vector b is different. So they're really independent. And the conjecture we want to make is that there's no bulk discount. You can't solve these any faster than you could one at a time, right? Just having them next to each other when they're completely independent isn't helping you solve them any faster, which I don't know if that's a reasonable conjecture, but that's what we're saying. And if that's the case, then the calculation is pretty simple. Each one of these takes t to the omega time. You have n times t of them, so n t to the omega minus 1. That's why we think this is optimal. All right. So I think I'll skip over the extensions and maybe end there. Whoop. Thank you.
Thanks for the very nice talk. Questions?
Well, as I'm sure you know, nested dissection also works for three-dimensional grids. So what can you say about three-dimensional grids?
I don't know. I mean, I guess the tree width is like n to the 2/3.
That's the separator size. I don't know what the tree width is.
I don't know exactly. I would assume probably n to the 2/3 omega, but that's a guess.
So then the complexity is, so the separator size is n to the 2/3, and then we have to cube that, so you get n squared complexity for a three-dimensional grid with nested dissection, I think. So how does yours compare in that case?
Well, just an omega instead of the 3, I think. So slightly smaller. But I would have thought nested dissection got the omega, right? The omega, it's in the planar case. Yeah, sorry, I'm not 100% sure.
So when you do the reductions, it looks like you're doing potentially doing mostly sparse linear algebra. So given that you showed that there is certain reductions between system solving and other linear algebra operations, would there potentially be any benefit in analyzing if the subproblems you're working on are sparse systems and then trying to bootstrap your algorithm in, so recursively running your algorithm on the smaller instance?
I think I have the opposite intuition, that the small problems that we're solving along the way are actually dense. Or if they're sparse, it's not meaningfully so, maybe half filled or something, but you're not going to get an asymptotic speed up from it. I don't know. After a few rounds of going up, you can make a complete mess with these systems, right? So even if it looks like you're getting in sparse structure from the original matrix, it might not be, I think.
So have you thought about constructing a tree decomposition that sort of works best for your algorithm?
Yeah, that's an idea. Tree width is normally defined in terms of the width, which is a maximum. And you could just directly aim to minimize the sum of the omega powers or something. I don't know if that meaningfully changes anything. We've thought about it, but that's as far as I've gotten. It's a good idea.
You have this problem you had at the end where you had lots of copies of the same problem, but you also have this assumption earlier about operations being unit time.
Yes.
And I'm wondering how these two things play together, because if I was working over a finite field, I would assume that having a lot of problems over the same finite field of the same size, I could probably actually get speed up.
Yeah. You'll notice that I say characteristic 0 here, and that's exactly why. If you accumulate enough problems, exponentially many, you could just write down all the linear algebra problems of size 3 by 3 on F2 entries or something, and then just look up the answer rather than recomputing.
Now that seems to go against the assumption of operations being unit time. I mean, they're getting costs because of, they're getting complicated numbers, and I don't know how to reconcile this with that.
Yeah, I'm not sure either. Yeah, it's a bit of a mess, but seems like it should morally be true, and this conjecture, and you just have to work out the details of what exactly that means. It might involve, you know, can you cheat by using unit cost operations to do more than you should, or something like that. That's entirely possible, but anyway, it's just meant to give an intuition that our result is the right bound.
All right, let's thank the speaker.